Hello students. Yesterday I have discussed some problems on charge distribution on the plates placed in very close vicinity. From that trail, I shall today discuss one problem on charge distribution, and then I shall discuss some conceptual and minor tricks will be there. Some numericals and some MCQs. Okay? So let us start. Two large plates X and Y are placed in close vicinity. Find charge distribution on the surface. It was placed in a exam in form of MCQ, but to save time I did not present it as an MCQ. Just right answer A, B, C, D. Is all. You have to find the charges on these surfaces. Try yourself. Yesterday I have given you two tricks. Outer surfaces of combination must have outer faces must have same charge. Outer face must have same charge. Okay. Faces or surfaces facing each other. Surfaces facing each other. Will have equal and opposite charge. Will have equal and opposite charge. Equal and opposite charge. On this basis, you solve the problem, and I think you will be able to solve it in minutes time. Perhaps you have already solved it. Let us consider that B has charge Q dash. Then from conservation of charge, what will happen? 2Q minus Q dash will be the charge on A. These two faces are opposite, surfaces are opposite, facing each other. So here there will be minus Q dash. If this is minus Q dash, these two are outer surfaces. These two must have equal amount of charges. Problem solved. Now you apply conservation. This is isolated body. You apply conservation on Y plate. Total charge 2Q minus Q dash minus Q dash. This will be equal to minus Q. This will be equal to minus Q. Problem solved. Twice Q dash equal to Q. So Q dash equal to 0.5 Q. Rest to do 0.5 Q. 0.5 Q. Here there will be 0.5 Q. 0.5 Q. 2Q minus 0.5 Q. 1.5 Q. Here there is 1.5 Q. 1.5 Q. Problem solved. It did not take even 1 minute. Next problem. Let us take another problem. Very easy problem. I forgot to tell you that today's problem is particularly very useful for NEET, very useful for NEET, and also for JEE. But it is more useful for NEET because problems are not so complicated. Here there is a square thing. Potential of A, B, E and D. A, B, E and D are given. It will be 2 volt, A 2 volt, B, E, D each 5 volt. 5 volt, 5 volt. Electric field intensity. The region. 4 options are there. 10 volt per meter along PQ. 15 volt per meter. 4 options are there. What concept you have to apply? You know, you try yourself. Minus dVdx. What does it mean? That it means that electric field intensity is in direction of decreasing potential. In direction of decreasing potential. This thing you have to remember. Decreasing potential. Okay. This thing you have to remember. But problem solved. You take a pause and try yourself. Which option will you? Try. This has A has 2 volts. This has 2 volts. And this has 5 volts. 5 volts. This is 5 volts. Yeah, this is in this direction. This will be straight. So potential has increased. That means it has decreased in this direction. So direction of potential will be. This is also 5 volt. This is also 5 volt. Direction of potential. This is the distance between two potential points. Two potential points. What will be the distance? PA 0.1 meter, 0.1 meter. That means P is equal to root 2 into 0.1 meter. Or you write it 0.1 into 2 meter. Okay. So potential electric field intensity will be potential difference by distance. Potential difference 5 minus 2. 5 minus 2 divided by distance. 0.1 root 2 into root 2. So 3 by 0.1 into root 2, but 30 by root 2, that means 15 root 2. And so volt per meter. So which option will be there? This direction and electric field intensity 15 along PA direction. 15 root 2, only 15 root 2 will be the option. So you can, without understanding, you can keep it 15 root 2 volt along PA. Along. Okay? That is the problem. Very small tricks are there. If you know E equal to dVdx minus dVdx, no problem will be there. These are very handout problem. You have to within few seconds or 15 or 30 seconds you will be able to solve the problem. Let us go to the next problem. Okay. Figure shows two conducting thin concentric shells. Two conducting thin concentric, one larger and one smaller. Of radii r. This is radius r and this is radii 3r. 3r. Outer shell carries charge q. Only outer shell. This is 3r and this is r. Outer shell. It is open. Outer shell carries charge q and inner neutral. This is neutral. When K is closed, amount of charge that will flows from inner shell to earth. If I close K, what amount of charge will flow from inner shell to earth? That I have to find out. Okay. What is the concept behind it? Concept is anything earth will have potential 0. That is the concept. Okay. So you try yourself on this concept and find the answer. See, when this is open, there will be no charge, because if you apply Gauss's law conducting, if you apply Gauss's law and I consider it as Gaussian surface, all flux will go out there, and will reach the earth. But when I close K, this is also the part of earth, and some flux will reach here. So this will be also charged. Okay. So K is closed. After closing K, let charge on this inner shell is Q dash. What will be the potential of inner shell? Potential of inner shell after closing K. What will be? For Q dash, surface potential will be K into Q dash by R. For Q, everywhere will be same potential. You consider there is no inner shell. Then what will be the potential? Everywhere will be same. Intensity is 0. So, and same potential will be equal to the surface potential. So Q, KQ divided by 3R. This is the potential of the inner shell after earthing. But this potential will be, this potential as earth V is 0, as earth V is 0. Then what is, so K Q dash or K Q dash by R is also cancel out, plus equal to minus Q by 3, equal to minus Q by 3. So when earth charge on the inner shell will be minus Q by 3. If it is charged to minus Q by 3, where from the charge will come? Charge will come from earth. So electron will flow from earth to inner shell. Then current or the positive charge, we consider it charge as positive. So positive charge flow from inner shell to earth. What amount of positive charge will flow? Q by 3. So not minus Q by 3, mind it, this will be Q by 3. Okay. Go to the next problem. Yes, let us go to the next problem. This may appear somewhat confusing those who are slightly nervous. A non-conducting ring of radius 0.5 meter has charge 1.11 into 10⁻⁻10 coulomb distributed non-uniform. Distributed non-uniform on it. The value of integral minus E dot dl L equal to infinity to L equal to 0. L equal to 0 means center of the ring. Here L equal to 0. And here. This in bold is 4 options are there. This is a slightly tricky problem. If you go by the definition, what is the definition? In this context, as it is written L, I shall write dV dl. Vector quantity, V is scalar quantity. So dV, this is equal to minus E dot dl. You are integrating infinity to 0. That means you are taking coming from infinity to this point. Then what will be? This will also be infinity to 0. So this is V infinity to 0. That means this is the value of this integral. I have to find out value of this integral. Okay. No brainstorming. So this is upper limit 0. That means at center potential V0 minus V infinity. You know V infinity equal to 0. So this is the value of this integral. So integral, value of integral. What is the value of integral? Value of integral from VO, that is potential at the center. To confuse you, it has been written non-uniformly, no difference whether, as regards potential, there is no difference whether it is distributed non-uniformly or uniformly, because distance is same everywhere. Here there is Q, here there is Q dash. So Q will give potential Q by R, this will give potential Q dash by R. R is same everywhere. So total potential will be summation of Q dash, Q. That is the summation. That means total charge Q divided by R. What is R? So GO equal to K Q divided by R. K means 9 into 10 to the power 9. What is the value of Q? 1.11 into 10 to the power minus 10 Coulomb in SI unit, and the radius being of radius 0.5 meter. Problem solved. So 0.5, that means half, multiplied by 2, 18 into 1.11 into 10 to the power minus 1. This volt is my answer. If you multiply it, that means 18, 8, 1, 10 to the power minus 1, that means 1.998. So which option will be correct? A option. It is nearly equal to 2 volt. So nothing is there, but some students may get confused by this presentation. Non-uniformly, minus, that is the definition. V equal to minus dV, E equal to minus dV. From this definition, I shall arrange it in this way: dV infinity to 0. Okay. Go to the next problem. Let us go to the next problem. This is very easy one. I am confident that everybody of you will be able to solve the problem. As in figure, charge Q, small q, is placed at the center of hemisphere. This is hemisphere. A second charge Q is placed at any one of the positions A, B, C, D. At any one position, I can keep capital Q. In which positions of the Q flux through hemisphere will remain unchanged? In which position of the Q flux through hemisphere will remain unchanged? During discussion of flux, I have told you that flux entering is negative and flux going out is positive. On that basis, on that concept, you solve the problem. You take pause and try to solve. Let us take the problem. For B, charge will enter, flux will enter and go out. So, some negative flux will be taken into account. For D, case is the same. Some flux will enter, but it will not going out of the hemisphere. So, this will be taken into account as negative. So, these two will change the total flux due to Q. Total flux due to Q is Q by epsilon. Here there will be 2 epsilon as it is hemisphere. Q by 2 epsilon. But with this negative flux will be added. So will not remain unchanged. Flux, amount of flux will not remain unchanged. So these two options are cancelled out. These two options are cancelled out. Okay, try the next two. C, the flux will enter this way. So it is entering in the hemisphere and also going out of the hemisphere. metallic body, it is going out, entering out. Any flux that will enter will also go out. It is entering and is going out. For any flux, this will happen. So C is correct option, and similar is the case for A. So what will be the option? D option is the correct option. Okay? So very easy one. Let us go to the next problem. This is an imaginary cube. This is an imaginary cube. That means it is a Gaussian surface. This is a Gaussian, consider a Gaussian surface. This is a rod, uniformly charged rod. This rod is entering this cube with velocity v. At t equal to 0, position of the rod is like shown on the figure. As shown in the figure, at t equal to 0, left end of the rod just touches the cube. Which of the graph shows variation of the flux phi to the cube versus flux going out from the cube versus the okay. Very easy problem. You pause, take pause and try. This type of problem usually comes at t equal to 0. It is there. After time t, length of rod in cube, what will be the length? Vt. তাহলে charge within in cube, how much? Lambda Vt. But what is lambda? Lambda linear charge density. Per unit length charge is lambda. Linear charge density. Okay. So this is charge in cube after time t. This is charge. So flux from cube phi, which will be q by epsilon 0. Q by epsilon 0. That is lambda v t. This is q by epsilon 0. Lambda and v are constant. So phi equal to kp. K is a constant. That is equal to lambda v by epsilon 0. Okay? K is constant, that is equal to lambda. So this curve is like straight line. So you may this cancel. This is also. This is there is also straight line here, there is also straight line, but this is somewhat complicated. What will happen? This is L by 2. So after entering the L by 2 length, charge within the cube will remain constant for some time. For how much time? It will take P dash equal to L by 2V. This time will be taken to enter into the cube and to reach the right end. So this straight line graph will be up to this, and this time is L by. How much length has entered within the cube? L by 2. So for next, until the rest L by 2 enters, there will be no change of charge. So this name is also L by 2V. That means this is L by V. So L by 2V to L by V, flux will remain constant. Then when it will come out, it will again decrease. Going out, so it will decrease. Already phi 0, phi flux has entered. Suppose phi flux has entered. Then it will decrease. Flux will be then Vt by Vt lambda divided by epsilon 0. So this will be a phi minus this is phi dash. Okay. Already phi has been, suppose phi 0. After entering the total L by 2 length, flux coming out is phi 0. Then phi 0 will gradually decrease and phi will vary like this. This is y equal to minus mx plus c, y equal to minus mx plus c type curve. That is this curve. So, which option will be right? C option will be right. Okay? Go to the next problem. Next two problems I shall place. These two problems will be identical in style. Okay. Very easy problem. Perhaps everybody of you will be able to solve it, and also I think you have also faced this problem. Yet I am placing it before you. It is a regular hexagon. Distance of center of hexagon C from any vertices is A. This is A, this is A, this is A. There are 5 charges placed at 5 places. You have to find electric field intensity at the center. Okay. This type of problem you will negotiate like this. Let us take a charge plus Q. System will be disturbed, but if I take minus Q, system will remain unchanged. This plus Q and this phi will make electric field intensity at C 0. Rest remaining charge minus Q will produce electric field along this direction, that is minus along this direction. What is the electric field? 1/4 pi epsilon 0 Q divided by square. This is the answer. Okay. It is time to go to the another like similar problem. Let us take the next problem, and this will be my last problem for the day. This is a conducting thin shape. This is thin shape, the sphere. Surface density of charge has surface density of charge sigma. A small hole is made at point P. What will be the electric field intensity at point? 4 options is trying to solve in similar style like previous one. I shall give you a hint like this. In similar style like previous one. You take a pause and try yourself. Suppose hole has not been made. This is a conducting shell, surface density of charge sigma. What will be the field intensity? No doubt sigma by epsilon 0. We know it because inside there will be no flux. Inside there will be no flux. Okay. I have told you a problem. Suppose this is positively charged. This is negatively charged, and I have placed a metallic slab here. What will happen? Negative charge will be collected here, positive charge will be collected. As this is metallic, there are innumerable number of electrons. There is no dearth of want of electrons. So this field will be neutralized by this field, and this field and this field will cancel out. It is also E, it is also E. So there is no electric field. Similar is the case for here. Suppose at this point it is a this sigma, this E is for this sigma by 2 epsilon and for this sigma by 2 epsilon, that is sigma by epsilon in same direction. So suppose this is a small conducting plate. What will be the charge? It can be considered as a thin sheet of charge. So in this direction there will be sigma by 2 epsilon 0. In this direction there will be sigma by 2 epsilon 0. Okay. diametrically opposite in this direction, sigma by 2 epsilon 0. For this, actually this does not depend upon distance. So for this, suppose this is A part and this is B part. So here this one is for A part and sigma by 2 epsilon 0, sigma by 2 epsilon 0 will be for B part. This is the condition, and these two has cancelled out. This 2 has cancelled out, and this sigma, it is 0, but due to this sigma by 2 epsilon 0 EA and EB, due to this B part, here also sigma by 2 epsilon 0. So total electric field from this is sigma by epsilon 0. Right? Now consider what will happen if this is out. This is out. What will happen? Due to EA, this will be no more, this is 0, only EB will be present. So after making whole, what will be the electric field intensity here? Sigma by 2 epsilon 0. Have I been able to make you understand it? Again, consider this point. For this B part, here electric field sigma by 2 epsilon 0. When there is no hole, this is for B part. Again I am explaining. And for A part, again it is sigma by 2 epsilon 0. Total sigma by epsilon 0. But when I shall make a hole here, this will be absent, and only field will be EB equal to sigma by 2 epsilon 0. That is my option C is right. Okay, that's all for the day. I hope you all have enjoyed this class. Today's class is very light class, and no problem was very complicated, but these are very, very suitable for NEET and also for JEE students. Okay, that's all. Until next class, goodbye.